Alright, so today we are going to be looking at kinematics. We're going to be focusing on one-dimensional motion. So when we start looking at kinematics, we need to look at the difference between position and displacement. Position would basically be where you are in a coordinate system, if we had a defined system. Our displacement is the change in that position. So if we are looking at a linear direction where we are moving only in a straight line, then what we are dealing with is we are dealing with displacement being the change in position. Where you end minus where you started. So it's basically final minus initial. So displacement is a vector. That means it has both a magnitude or a size, and it has a direction. Now, if we are looking at an angle, that's from the standard direction, so that means from the positive x-axis, we would measure up for that angle. Or it could be something as simple as north, south, east, or west. The displacement is independent of the path traveled, so it's, as we say in our rural areas, it's as the crow flies, where you start to where you end. So, we deal with displacement in our current situation. We're looking at particles, so point-like objects, or objects that behave like a point-like object. So let's start by looking at some of these displacements. So here we have some coordinates, and we want to know which ones give us a negative displacement. So we're going to create our axis system. So here I've got 0, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So we're starting at -3 and we're going to 5. So where we start to where we end as the crow flies. So this has a positive displacement of 8 meters. If we look at our next one, we are going from -3 so here is 1, 2, 3, -3, so this is our starting point. And then we are going back to -7, so -7 is over here. So where we start to where we end. So that's giving me a -4 meter displacement. Our last one, we have 7 meters and -3 meters. So we are starting here at 7 meters. We are ending at -3. So from where we start to where we end, we have a displacement of -10 meters. So our two that give us a negative displacement are B and C. So displacement tells us where we've gone from our starting point, but we need to know how we got there. And that's where average velocity comes in. Average velocity is our displacement divided by the time in which that takes. So velocity average is in the same direction. It is a vector that is in the same direction as the displacement. So it's basically pointing us along that path. So if we look at a position versus time graph, we can find the average velocity. Now how could we do that? Well, if we have a position versus time, and we could find our average velocity by looking at the slope of the secant line between those points. So if I play connect the dots with the straight line, I can look at the rise, which is going to be my change in x, over the run, which is going to be my change in time. So our slope is going to be rise over run, which is change in x over change in t. So that is right there, gives me the average velocity. Okay, so let's look at this example. So here we have an armadillo, and he is going from basically 0 to 4 seconds. And we want to know what is his average velocity from 1 to 4 seconds. So the first thing that I need to do is I need to make kind of a secant line here. Okay, so here is my secant line. Now we need to look at the slope of the secant line. So the average velocity is going to be the rise over the run, so the change in x over the change in time. So in this case, our x up here is at 2. Our x down here is at a -4. Our final time is at 4 seconds, and our initial time was at 1 second. So that's going to get me 6 divided by 3, which is 2 meters per second. So that is my average velocity over that time interval. Now, does it mean the armadillo is going that speed every single second? No. So speaking of speed, speed is the total distance traveled over the total time. Now, it may or may not equal the average velocity. So here we're looking for the total distance traveled. Well, he's gone from -4 to 2, so he's traveled 6 meters. So his total distance is 6 meters. And we want to know the time in which that takes. Well, that took 3 seconds. So our speed in this case, our average speed is 2 meters per second. It does happen that this is exactly the same. However, it does not have to be. That is not a requirement. It is not a requirement that they have to be identical. There is another type of velocity. We refer to that as instantaneous velocity. Oftentimes we'll just drop the instantaneous and just say velocity. That is your velocity right at a given point in time. So this velocity is a vector. Specifically, it is our direction of motion. So oftentimes what we're doing is we're looking at the average velocity, but we're taking that time interval to be super tiny. And that is what gives us the piece that sets this physics apart, which is that derivative component. So as we look at a position versus time graph, the slope of the tangent line gives us information on the instantaneous velocity. So if we want to look at the armadillo at 1 second and at 3 seconds, so let's go back to our armadillo graph here. So if we look at 1 second and we have a small tangent line attached at that point, and we look up here at 3 seconds and we put a small tangent line attached at that point, and we look at the slopes of those individual tangent lines, that's going to give us the slope or the velocity of this armadillo as it goes through 1 second and as it goes through the 3 second mark.